This video is about some of the most important parts of Chapter 7. So let's first get to that chapter. And as always, make sure that you check out the videos that are at the beginning of each section. So if I scroll down, here we go, starting on page 426. You know how there's always these video introductions to each section. At a minimum, always watch those, and definitely if you feel like you need to explore some of the videos for specific examples, please do so. But this particular section is about the basics of probability. So I'm going to start on page 429. Here we find the theoretical definition and formula for probability. And you'll use this formula and a very similar formula for relative frequency probabilities. You'll find out that they're really the same. It's the number of ways that an event can occur out of the total possible number of outcomes. And they can be expressed as a fraction, a decimal, or a percent. On page 431, here we find a definition, or a brief review rather, of the multiplication principle. Now, I will sometimes call this a counting principle as well, but this is going to be expanded on in a later chapter. So it's really important that you go through and understand this process and basically the formula that's presented here as well. On the next page, we see the definition for the relative frequency method. So this is like as if we've run an experiment and we have the number of times an event occurred out of the total number of times we ran the experiment. But you see it's very similar to the theoretical definition, and that is on purpose. On page 434, here's another definition and formula provided for a probability of an event not occurring. And so if we know that the probability of all events, all the possible events, would sum to 1, and we want to know the chance that an event won't occur, then we subtract the probability that it will occur from 1. So for instance, if I know that the probability that an event will occur is 1/4, then the chance that it will not occur is 3/4. 1 minus 1/4 is 3/4. And that's the way that definition works. This is kind of a definition that sometimes we forget about, but is very important for finding probability. So make sure that you have that in your toolbox. Later, let's see, on page 436, we have a definition for odds, which is a little different than the way we describe probabilities. So for instance, the odds for event A is the probability that event A occurs over the probability that event A does not occur. All right, and I believe that's it for that particular section. So I'm going to move on to page 442. In this next section, we look at the difference between independent and dependent events. And here you have a definition for independent events. And basically, independent events are events that are not determined by a previous event happening. So, in other words, the probability that an event occurs does not depend on the probability of a prior event. On page 443, we see how to find probabilities of independent events that use the word and. So for instance, if I know that two events are independent and I want to find the probability of A and the probability of B, then I can multiply those individual probabilities together. That's a really powerful rule and formula that you'll use here. On the next page, we see the definition of dependent events. So the difference here is that a dependent event has a different probability because it depends on what happens prior to that event. So I like this example here where we see this box of candies or chocolates, and the probability of choosing a chocolate candy is 5 out of 10. There are 5 chocolate candies out of the 10 total candies. But once one of those chocolate candies is gone, then there's a different probability because now there's only 9 candies left, 4 of which are chocolate. So it depends on that prior event. Those are dependent events there. And there is a formula on the next page for this. So I can still find the probability of 2 dependent events, the probability of A and B, but I have to determine the probability of A times the probability of B given that A already occurred. So just make sure that you're watching for that there, that you take into account that A has already happened. There is a little bit of notation over here, by the way, but we don't have to be too formal with that notation. You can use that written word given there. That's fine. Also on the next page, we see the difference between non-overlapping and overlapping events. Sometimes they're called mutually exclusive events if they're non-overlapping. So for instance, when we toss a coin, it's either going to be heads or tails. It cannot be both. So that would be an example of a non-overlapping event. And if you want to find the probability of non-overlapping events combined with the word or, then we would add those individual probabilities together. But they must be non-overlapping in order to just add them together like this. A little bit further down, we see that there are such things as overlapping events. So, for instance, I like this example of using cards because a card contains a color and a suit and either a face or a number value. So there's lots of things that a card could be. It's more than one thing. So there are some possible overlaps in that particular example. And on the next page, we see the formula for finding the probability of overlapping events. Notice that it starts off similarly. The probability of A or B is the probability of A plus the probability of B, but we must subtract the probability that A and B occurs. And again, I like the diagram that's above it because the reason we're subtracting is because of that overlap. In the next section, I'm going to skip ahead to page 554. Here we have the definition of law of large numbers. That basically says that over time we should expect that the proportion we get from a single trial or repeated trials should be closer and closer to this theoretical probability. And there's some interesting examples as well in this particular section I encourage you to read through. I think this is also the section that had the piece about gambling and how that could be applied. But I'm going to skip ahead to 456 because there's one other formula here I wanted to note, and that is expected value. So the expected value of an event is defined as the value of the event. So that could be usually a dollar amount times the probability of that event plus the dollar amount. Again, it doesn't have to be dollar amount, but it's normally something like that, of the value of event 2 times the probability that that event happens. So notice there's a combination here of operations. Just pay close attention to that as you use that formula. In the next section, I didn't write down the page number here, but in the next section, we see some experience with real-world examples. I think that one would be, skip ahead. yes, this, well, actually, I think it started on this page down here at the bottom. Assessing risk. So no real formulas in this particular section, but these are a lot of good real-world examples. Go through and read those and see how we can apply these types of probabilities in real life. All right, so now I'm going to skip ahead to the last section. Starting on page 477, there is a definition for permutations. And really this section is that deeper dive into counting the number of outcomes. And we have two different ways that we can count, depending on if order matters or if order doesn't matter. So here, this permutation formula is how we would count a number of arrangements if the order of the arrangement matters. So for instance, I like to use the example if you're running for, let's say, or maybe in a competition where there's a first, second, third place, order matters there. So if person A gets first place, person B gets second place, and person C gets third place, that's different than if it's person C who gets first place, right? So in that case, order matters, and you would want to use the permutation formula. The other side of that is if order does not matter, and that's on page 479. These are called combinations. So I like to use the example of selecting members of a committee. Usually on a committee, everybody has equal power. So there is no first, second, or third place person, right? Everyone has the same amount of say in the committee. So committees that consist of person A, B, C is the same as a committee that consists of persons C, B, A. And again, here you see that formula. Notice that along the way, there are some technology tips here, how you can use your calculator to help you find combinations if you don't want to have to go through the longer formula. And last but not least, I just want to point out on page 487 is the summary of all the formulas in this particular chapter for a quick reference. Don't forget to click Ask My Instructor if you've got any questions as you progress through this chapter, and I'd be more than happy to help.